Okay, so in this video I'm going to go through the, selected questions from the Stats 1 paper WJC June 2010. So I'm going to start with question number 1. Makes sense to start at the top. 1A. So it tells you that you've got two independent events, A and B, such that probability of A is 0.6 and probability of B is 0.3. And then tells you to find the probability of P, A union B. So these are independent events. It might help to draw a Venn diagram here, as much as I personally hate them. Let's choose a nicer colour. This will do. Okay, so we've got two independent events, A and B. Now what this means is the occurrence of one does not affect the probability of the occurrence of the other. This doesn't necessarily mean they can't overlap. So our Venn diagram has to look like this, where this is event A and this is event B. So the probability of A being in union with B is the probability of A plus the probability of B but then this middle section here has occurred twice because it's in both A and B. So we have to take that away, minus the probability of A intersecting with B. Now all of this, probability of A plus probability of B is 0.9, and the probability of them both occurring is the probability of one occurring multiplied by the probability of the other. That's 0.6 multiplied by 0.3, and that's 0.18. So this is all going to come to 0.72. That's question 1A done. 1B, it tells you to find P, A union not B. Now there are a couple of ways we could do this, but let's just go back to our diagram and I'll lose this. Oops, let's just get that back. There we go. And I want to get rid of this little yellow bit in the middle there. So P, A union not B. What are our probabilities? Let's just label them. Well, we know this central section of the diagram here, this bit, this is 0.18. And A is 0.6 in total, so this must be 0.42. This must then be 0.12. And the rest of this area will be whatever 1 minus all this is, so that's 1 minus, 0.72, which is 0.28. So just looking at our Venn diagram, we're now just looking for all of the area that's not B, because this means A or not B, or both. So we're looking for this entire diagram minus this area here, which is 1 minus 0.12, which equals 0.88. And that's question 1 done. Now to move on to question 2. So in question 2 we're now given some random variables to deal with. So this is the random variable x, and it has mean of 4 and variance 3. So the random variable y is given by 3 lots of the random variable x minus 1, and we're told to find its mean and its variance. So the mean, or the expected value of x, is literally just going to be plugging the mean of x into this formula. Oh, sorry, this is the expected value of y now. We're given the expected value of x, that equals 4. The expected value of y, then we just plug x right into this formula. And that's just going to give us 11. Now, when we're trying to find the variance of y, that's not so easy. The variance of y, well, this is all about the deviation of y. And that's not going to change with this minus 1, because that's done to all the numbers in the same way. it only changes with this 3x bit. And that's because we're multiplying by a number, but the number we're multiplying is changing, so it's a scale change, if you like. So to find the variance of y, what we do is we take this and we square the coefficient. So, and then multiply. So we do 3 squared by the variance of x, which is 2, and we end up with 18. And then we're told to hence find the value of the expected value of y squared. Now, a little formula that you can look up or you might know is that the expected value of y squared is equal to the variance of y plus the expected value of y squared. So notice we're not squaring in the brackets here. So this means if we squared 3x plus 1 and made that our new minus 1 and made that our new y, this is what we'd get. And this equals 18 plus 121, so that's 139. So that's question 2 done. Question 3 I'm going to skip because it's not on the mandate. I've got the questions I've got to go through. So question 4. Okay. This is a nice probability question. It's relatively easy for the first 2 parts at least. So 4a. Find the probability Bill wins with his first throw. So this is the probability that Alan misses, multiplied by the probability that Bill hits. And by the way, I'm just going to say that P of Bn is just the probability Bill wins on his nth throw. So this is just 0.2 by... 0.8, it's 1 minus 0.2, so 0.8 by 0.3. And 0.8 by 0.3 is 0.24, so that's our probability of Bill winning on the first go. The probability of Bill winning on the second go is going to be the probability that Alan misses, 0.8, times the probability Bill misses, 0.7, times the probability Alan misses again, another 0.8, times the probability Bill hits, which is 0.3. And if I do my maths right, all of that comes out to, I think, 0.1344. That's part B done. Now part C is an interesting part. And the way I opted to do this is using a geometric progression. And the reason is you're told to find the probability Bill wins the game. Now, there's no guarantee that this game will ever end. Alan and Bill could, in theory, keep missing forever, meaning you've got an infinite number of events to consider. And then I noticed that each event, what we've done to get from here, this bit here, to get to here, all we've done is we've multiplied by some set of numbers. So we could say that P of B2 equals P of B1 times R, some common ratio. So what does R equal? Well, the first thing we have to do is say that in the probability that Bill hits on his first go, Bill has hit on the first go. In the probability Bill hits on his second go, he hasn't hit on his first go. So we have to first divide P of B1 by the probability Bill hits. That's 0.3. or 3/10. Now we want to multiply by a common ratio R, so that's the same as saying multiply by 10/3. Then Alan has missed, that's multiplied by 8/10. And then what has happened? Well, we're assuming that Bill misses the first go, another go as well, 7/10. And then we say now that sorry, this is in the wrong order. Really, we're saying that what happens is, my bad, we change it so Bill hasn't hit, then we make it so he's missed, that's 7/10. Then we make it so Alan has missed on the next go, then we make it so Bill has hit. And that seems long, but the end2 cancel out and you just end up with 0.56 for your common ratio. Now, here we've stated it for an individual case, but what we can actually say is the probability that Bill wins on any go on the nth try equals the probability he wins on the first try times r to the power n minus 1. And if we call the probability he wins on the first go a, that's our first term, suddenly this is just a geometric progression, and we can say that the sum to infinity equals the probability Bill wins. Probability that Bill wins, and this is quite easy now because we just do a over 1 minus r. A is 0.224 and 1 minus r is 0.44, and this comes out as 0.54 recurring. And that's for C done. It was just seeing that you could do this with a geometric progression with this method that gets you through it quite easily. If we take a new page now. So question 5 is the next on my list. So this is about a quiz game with some character Jack. Calculate the probability that Jack gives the correct answer. Well, this is just the probability he knows the answer plus the probability that when he does not know, he guesses it right. So the probability he knows the answer is 0.6. The probability that he guesses it right, because there are 4 options, is a quarter. However, he only makes a guess 0.4 of the time, so this is 0.4 by 0.25. This is just, so he knows the answer, he doesn't know the answer, but gets it right with his guess. And this all comes to 0.7. Part B, well, given that Jack gave the correct answer to a question, find the probability he knew the correct answer. So, this we're trying to find the probability he knew the answer, given that he gave the correct answer. Well, we can again think of this in a Venn diagram, so let's draw another one of those, in purple this time. So, what's actually happening here is we've got him giving the correct answer, is this bit. Him knowing the answer is a very large proportion of this bit. This is the probability he knows the answer. And then him guessing is this other bit. So, when we just give the probability he knew the answer, that's 0.6, we're saying this is 0.6 of this whole Venn diagram, of this whole 1. But we already knew that actually all of this part outside of these 2 circles, that's irrelevant, because we already know that he gave the correct answer, that it's in these 2 circles. So we need to narrow our field, and the way we do that is by dividing by the size of that field, and the size of this field is 0.7. So the answer is 0.6 over 0.7, or 6/7, which I'll leave in a fraction because it's a recurring decimal with like 5 or 6 places. Okay, question 6 is next up, and there are a couple of parts to this. So 6a is show that k equals 1/16. Well, we know that the sum of all probabilities of x equals 1. So that is that in this question, kx, where the probability of x equaling some value equals kx for x equals 1, 3, 5, and 7. So therefore we know that 1k, oops, let's make this now, k plus 3k plus 5k plus 7k equals 1. This is 16k equals 1, so k equals 1/16. That's that bit done. Part B. So determine the expected value